Okay, good afternoon. Are there any questions before we start? Was the homework long or it was long?
Yes.
I hear that it was long. Yes, I can agree with that. I surely can agree with that. And let me just say that the next homework is no shorter. So that is equally long. So I would suggest to start soon and not wait until last couple of days. Okay, it was long. Was it thought-provoking? Did it make you think or not so much? I mean, long and boring isn't very good. But long and thought-provoking is more useful. Okay, I see some nods. Okay, so we spent a lot of time talking about real FFT and how the n-point real FFT was computed using n by 2 point complex FFT. So today I want to spend most of the time talking about how the FFT structure itself can be optimized when the signal is real, and that's what we are going to spend most of our time today. Did you finish your homework or you need more time to finish? I see you are not, it means you are done? Okay, I'm happy. I mean, if you want to turn it in a couple of hours late, that is perfectly fine. You can have up to 6 p.m. If you want to take a couple more hours, that's perfectly fine. Submit homework 2 by 6 p.m. in room 6181. So just push it inside my office and that should be okay. We will post solutions for sure within a few hours of that. Okay, homework 3, which we'll take a look before the class ends, is not any shorter. So, okay. So, how can we optimize the DFT when the signal is real? So, that's really our goal today. So, our main goal today is to talk about real FFT in two particular cases. First, in the context of DIT, DIF, and then in the context of composite FFT. So we will take a look at both of those. I do want to spend a little time talking about radix, higher radix 2 squared, 2 cube, and things like that, but we'll see. Maybe I won't be able to get to that today. We may run out of time, in which case I will get to those maybe next class, just briefly, maybe 5 minutes or so. Okay, so let's start with some simple examples of 4-point FFT. Okay, so okay, here is an example of 4-point FFT. So obviously, if we have 2-point FFT and if let's just step back and talk about 2-point FFT. Why? Okay, maybe I don't have a diagram, but that's okay. So for a 2-point FFT, here it is. So we compute the 2-point DFT of A and B as cap A and cap B, which are A plus B minus B. So if these are real, then both of these are real and there is nothing to throw out, there is nothing redundant, so there is nothing to throw out. If we have a 4-point DFT and if the signal is real, that means these are real, then there is something to throw out. because if we use the property that xk is conjugate of xn minus k, then what do you think will be redundant here? So if this was A, B, C, D, which will be conjugate of what? Is this something that can be thrown out? No, because that's just the sum of all of these, and if these are real, that's real. Okay, what about this? This is real, this cannot be thrown out. So why is that? Because that's real, this is real, these are all real up to here. The only imaginary is here, this is imaginary. Okay, so if we take that flow graph and draw the 4-point DFT, okay, I have placed a rectangle here just to indicate that these are purely real, this is purely imaginary. Okay, and then okay, so this dashed line means purely imaginary, and this so-called bold circle means it's complex. Okay, I'm just following some notations, but that's a way to understand. Now that last quantity D or x3 is going to be conjugate of x1, so there isn't really any point computing that, so that can be thrown away. So now if you think about the FFT or DFT is just a linear transformation. So one of the things to think about is what are the degrees of freedom. So in a complex FFT, if these were complex, then if this was some quantity plus j times some other quantity, there would be two numbers, and for n point complex FFT, the number of values would be 2 times n, because each complex sample would have a purely real part and a purely imaginary part. So when I'm talking about a real FFT, there is no imaginary part at the input, so the degrees of freedom should be n at every stage of FFT computation. So the degree of freedom in this example is 4. How many numbers are here after I have finished computing this? There are 3 purely real numbers, 1 purely imaginary, that's 4. And how many here? This is real, this is real, this is complex. So complex has 2 values, and so this is also 4. And so that kind of structure is called a canonic structure, a data canonic or canonic. So that means the total number of values at the intermediate stages and input stage and output stage is going to be n if it's the n point real DFT. Number of degrees of freedom is equal to n for n point real FFT. For the complex case, it would be 2n. So we don't want to stop here. The next thing I want to do is how do I really describe this so that it exactly looks kind of like the complex FFT. And the way to do that is really to not take that point. This point was not computing anything. It looks like half a butterfly, but it's not computing anything. It's just appending the real part and the imaginary part. Instead, what I can do is, so call this x1 real and this is x1 imaginary. And then that if you look at that, it's back to the same FFT type structure. It just so happens that I don't have a butterfly. That half a butterfly really doesn't. It's not a butterfly. It's just carry through signals. So we have n by 2 butterflies here and just one butterfly in this final stage. So that's what I would call the structure of a 4-point real FFT, which satisfies the data canonic property. Any questions about this? Okay, so now let's talk about how do we describe the 8-point. So let's think about 8-point DIT RFFT. So if I want to compute the DFT of 8-point sequence, so the DIT idea, this is the DIT idea, we compute the even and the odd, okay, and then merge. So here is the thing. So we start with, when I take that 4-point and this 4-point, already make sure that I take this as the 4-point. Okay, that means there is no computation of x3 involved, only x0, x1 real, x1 imaginary, x2. So if I just place that here and here, and then we will try to merge that. So this is the even part. Okay, so 0, 4, 2, 6. Those are the even parts. 1, 5, 3, 7. Those are the odd parts. Okay, now let's just paste the 4-point from the previous slide. Minus j No, I didn't copy it correctly. No, that's correct, yeah. Okay, so and then we had the second stage. Okay, so these are the 4 points. So let me just write down what these indices were like. So these were like 0, 1 R, 2, 1 I, something like that. Okay. Okay, so now once we have those things, what is the merge part going to do? The merge part is going to compute the butterflies of this. Yeah, that's the merge butterfly. So yeah, I don't think I have I should have 8-point complete diagram from our notes. I am not sure if I have, but anyway, so let's, well, there is something here at least, although not quite what I need. But okay, we'll do a quick merging operation. So the basics, so if we had DIT 8 points, so what does that look like? So we have 4 outputs coming out of the, so these are even 0, 4, 2, 6, odd, and then, so what do? We have the twiddles, W squared, W cube. So those are the twiddles, right? And so we have to have, after we have these twiddles, then we merge okay, that's how we construct the 8-point DFT by decimation in time. Okay, so now think about that we have thrown out this part, we have thrown out this part, so the third output of each, so the third output has been thrown out. So this has been thrown out from both of those. So which means that if that's thrown out, what does that mean? It doesn't exist. So if it doesn't exist, there's nothing to compute here, there's nothing to compute here, nothing to compute here. So these things are not computed. Okay, so ultimately we were going to compute, so let's take a quick look. So these were 0, 1, 2, 3, 4, 5, 6, 7. So we cannot compute 3 and 7. They have been thrown out. There is no way that we can compute these because these have been eliminated. Is that a problem? 3 is conjugate of 5, so okay, that's not a problem. 7 is conjugate of 1. I have 1, so that's not a problem. Okay. 0 and 4 are real, they have to be computed. 2 is conjugate of 6. 2 is conjugate of 6, which means that I really don't need to compute both of them. So try to throw out 6. So throw out 6. Okay. So usually we throw out, so out of xn by 4 and xn by 3n by 4. So n is 8, x2 and x6. So throw this one out. If I throw this one out, there is nothing to compute here. Okay. Okay, so there is nothing to compute here. This one will be computed. That will be computed. Okay, so now we have simplified what we need to keep and what we need to throw out. So let's go back to the previous diagram and see how I can connect them. So there isn't really much changing with respect to the first of each one of them, because so that's just simple. Let's see here. So in terms of, by the way, this w squared is minus j. This w to power n by 4 is minus j. In this example, n is 8, n by 4 is 2. So this really is minus j, which means that the real twiddle is only 1. So that whole w there is only 1. So that's okay. So now if I place these twiddles on the bottom things, next one is W. Okay, so we have, okay, so okay, and this was real, so well, this is minus j, so that twiddle is minus j, so that will become purely imaginary after it is multiplied by minus j. Okay, so now take a look at what I did here. Remember that this and this together are x1. This one and this one, this is the real and imaginary part. So I just group these together. I group these together. So that became this quantity that I need to multiply w, that 1. Think about that as output 1. So that w. So I merge the real and imaginary part together, multiply by w, then separate out the real and imaginary part. So the imaginary part is back to that bottom wire. The real part, I should say, this is that notation. If I'm going to indicate these rectangular boxes by the imaginary, then that's that notation. Okay, so now first, okay. So those are 0 and 4. Okay, so those are real. So we are done with that butterfly. That was the simplest thing. Now what's going on with the 1 and 5? Well, I'll get to 1 and 5, but let's take a look at 1 and 1 up here multiplied by w. Well, let's take a look at that. 1 and 5. Okay, what is 1 and 5? So that's 1. That's 1. And that's 5. So think about this. So here I had 1 real, 1 imaginary. After multiplying by w, think about this as 5 real and 5 imaginary. And now, so when I do the butterfly of 1 and 5, so that butterfly 1 plus 5, 1 minus 5. Okay, so that really says, so this is the real to real butterfly, 1 real, 5 real. Now the butterfly of 1 imaginary and 5 imaginary, and these are purely imaginary, is going to be 1 imaginary and 5 imaginary. Okay, so that's the last but not least is 2. So what's going on with 2? So we have thrown out 6. So 2, so this is multiplied by minus j. That's just adding real part and imaginary part. There's nothing to really add, so that becomes the 2 real. There's nothing to add, and this remains as 2 imaginary. So that completes the 8-point DITR FFT, which ultimately looks very similar to an FFT structure for complex FFT, but with less number of butterflies, less number of twiddles and things like that. Any question about this? So when I've asked you to do 16 points, so do the same thing, exactly same thing. So so just take this and paste this here. That's the 8 point, and paste this here. Take the even, take the odd, repeat this here and here, and then to design the merge circuit, you can always do what I did, but that's kind of what you have to do anyway. So and you will recognize that you can delete. So when you are doing 16 point, well, x12, you can delete x12 and keep x4. So is this satisfying the canonic property? So if you look at the degrees of freedom or the real number of actual samples, so that was 8. 6 real things and 2 imaginary things are also 8, and here 3 real, 1 more real, 4 real, 4 real, another real, 5 real. Okay, so 4, 5, 6, and these 2 8, and ultimately these are 8. So if you look at what has gone on here, we have computed 0, 1, 2, so eliminated. So we eliminated 3 and 7 from the first stage. I eliminated 3 here and 7 here. And then finally eliminated 6. So we eliminated 3, 7 and 6. And so you can see that the degrees of freedom are ultimately 8, and which is what we want. So we want to design canonic real FFT structures that satisfy that the degrees of freedom at each and every stage is n, or in this case 8. Okay, so these can be a bit involved. Well, these are, okay, I will say that these are involved, but I think that's kind of getting the hang of how to do these things. It's the whole goal, right? So let's take a look at how do we compute DIF RFFT. And again, let's take the 8-point example. Let me see if I have a complex FFT example, and that we can take a look. And I don't think. Well, okay, I can see that those things are in the handout that I had given you. Okay, so okay, let's try to see if we can even quickly draw this. So I seem to recall only we had W squared, right? So this should be minus J, and then um, I think, okay, if there is any mistake, we'll find out. Okay, so that's the 8-point DIF RF FFT. So this is W squared. W squared is minus J if n is equal to 8. All right, so when we started talking about what are the redundant parts to throw out, there is nothing to throw out here, and then we said, well, 2 is conjugate of 6, so we threw this one out, and then 3 and 7, 3 is conjugate of 5, and 7 is conjugate of 1, so we throw these out. Okay, so let's take a look. If I throw this out, I don't need that. I don't need that. I don't need that. Okay, so that's really what we can throw out. Half here, this whole thing, and then bottom half. So now if you look at so we really we are not satisfying the data canonic property because these are 8 numbers. Now here I have 5, but these are now complex. 3 times 2, 6. These are 6 numbers, these are complex. Plus 5, 11 numbers. Well, I said that wrong. These are 10 numbers. W squared is minus J. And that's really purely imaginary. So these are 10 numbers. And the only way that, before we proceed, the only way to make sure it's canonic is to shift this twiddle W, shift that to here, and W cube becomes W squared, which is minus J, and shift that also to here, so that becomes minus J times W. So this W, one W out of W cube, pushed out to the right here and here. I don't care about this because we have thrown this out. We don't even compute with that. So that minus J times W doesn't matter. Okay, so now what we are left with is, so now we have to simplify what's left. So all these top 6 are now real. These two bottom are purely imaginary. So now the degrees of freedom is still 8. If you look at this stage, 3 purely real, 1 imaginary. 1 complex here, complex because remember that was minus J. So this is really fully complex. So that's 3 plus 1, 4 plus 2 and multiply by twiddle. This is also complex. 2 plus 2, 4 plus 4, 8. And then how about the output with 3 out 3, 3 out 7. 0 and 4 are real. This is complex. And these two are real. So the number of degrees of freedom, 3 times 2 plus 2 is 8. So that satisfies the canonic property. And the last step that we need to do is to unroll or expand this half a butterfly to something like a real butterfly. But there is no butterfly involved. It's just take the real part and imaginary part. There is nothing being added. This is just appending real and imaginary part. This is, however, a complete complex butterfly, and expand that to be 2 butterflies, 2 real butterflies. When I say real, well, one will be for the real part, one will be for the imaginary part. And so if we are going to redraw this, so it looks very similar to the flow graph of a DIF FFT. Okay, so now, so far there isn't anything I have done, so everything is same as before. Now this one, if you look, this is really the appending the real part and imaginary part here, and we are not going to, well, okay, and they are going to be multiplied by that W. So I'm going to keep this as it is. I'm going to take the imaginary part as it is, and then, okay, I should be putting dashed lines, but that is then multiplied by W, and then the real part goes, and the imaginary part comes back, lines up with where it is. Okay, so that's that. No, I made a mistake. Okay, so the W is really to the next one, not that one. So this one stays as it is. Okay, that one stays as it is. So that stays as, take the real part and the imaginary part. The next one, so okay, I made some mistakes. We'll try to fix that. Next one is going to be multiplied by W, then the real part, and after W the imaginary part. Okay, so the 0, this real part goes straight forward, this imaginary part also goes straight. Okay, so now okay, so there was one twiddle that we multiplied. These two imaginaries are well, this imaginary just continues. That imaginary concatenates, multiplies by W, separates out. So what's the last step here? These are 0, 4. So 0, 4. Okay. The next one, something doesn't seem right because, okay, I see that doesn't seem right because that one is multiplied by minus J. So that's minus J, and that's purely imaginary. And then this is 2 real, this is 2 imaginary. Okay, so that's that half a butterfly, which isn't really any add or subtract of the butterfly. So that's just the real part is here, imaginary part is here. So we just take them straight. There isn't anything going on. Okay, so what about 1 and 5? So take a look here. So really, so the 5 I multiplied by W, okay, and then I have the real part, imaginary part, and then 1 was just the concatenation of the real and imaginary. So that's really corresponding to 1 real, 1 imaginary. Okay, so that's still 1 real, 1 imaginary. For the 5 real, 5 imaginary part, after multiplying by W, so now do the butterfly of the real part, 1 real, 5 real, butterfly of the imaginary part, and that's 1 imaginary, 5 imaginary. So that completes the canonic structure for the 8-point DIF RFFT. So for the DIF RFFT, a fundamental necessity is to push these twiddles to the right. So we have this minus J that then satisfies the canonic property. Okay, is that making sense? Yes, go ahead.
Is there a reason why you pull the imaginary ones into the real ones and do a full complex multiplication with W and pull them back out instead of just doing 2 like normal multiplications and put W on each of them? Is that question making any sense?
It is making sense, yes. I mean, what you are, okay, so there are 2 things going on. So one, I want to maintain the structure of the real FFT to look very similar to a complex FFT. So that's why I'm pulling it down. And now you're asking, okay, if I multiply W to the real quantity, that's 2 real multiplications. A times C plus ZD, that's 2 multiplications. If I take the complex or the purely imaginary B, just imaginary B times C plus ZD, that's 2 multiplications. 2 plus 2, 4 multiplications. Now if I pull it and append A plus JB, multiply by twiddle C plus ZD, and that's going to be, well, that's still going to be 4 multiplications. Yeah, well, okay, I mean, I haven't really reduced multiplications in that sense. I mean, there are tricks that I'm not saying now, but there are tricks that can reduce that to 3 multiplications. But yeah, that's what you were asking. You were asking.
Yeah, I guess the thing that I just thought of is when you, at the end, if you did them separately, you'd have 2 complex numbers.
We have two. It's not satisfying the data canonic property anymore. That's the real reason. That's the real reason. We are not going to satisfy the canonic property at the end of that stage. Number of degrees of freedom will increase by 2, which is what we don't want. Yeah, very good observation. Okay, excellent. Okay, so you will draw this a 16 point, again similar thing in your homework. It's involved. I mean, it's not that challenging, but it's easy to make mistakes, and that's why it can be involved. And you have to redo that diagram, and that means 20 minutes is lost. Okay, so what I want to do next is really talk about, we'll get back to some of these if there is time, but I want to spend time talking about how do we maintain the canonic property for composite FFTs. So composite FFTs, again, so let's take some examples. Let's say that I have. So by the way, these composite FFTs, the way you work them out will depend on different things. So if it is odd times odd, odd times even, even times odd, and even times even. So depending on which case it belongs to, you have to work through that in a slightly different way. But let's start with some simple examples. Let's say that we are going to start with 3 times 5 or 5 times 3. I'm not quite sure what notation we are using. But let's start with this diagram here. I have 5 point and then 3 point. Okay. So last but not least, we have these twiddles here, W squared, W cubed, w to power 4, w squared, w to power 4, w to power 6, w to power 8. Okay, so how do we maintain the data canonic property? That means the degrees of freedom at the end of this stage should be 15. After the twiddles is also 15, and at the output is also 15. So we should not have. I mean, right now, of course, it's all. It doesn't really matter. Okay, so let's start talking about how do we throw out the redundant parts. If you take the 5-point FFT, and let's just call this 0, 1, 2, 3, 4. Okay, 0 is just the sum of all of these. If I compute 1 and 2, then this should be thrown out, this should be thrown out, right? So 1 is conjugate of 4, 2 is conjugate of 3. So the last two should be thrown out, last two should be thrown out. So if I throw out last two, then these are thrown out, okay. Okay, so we have thrown out those things. These twiddles don't matter anymore, they're thrown out, okay. All right. So the first, all of these go to first, that's okay. But even here, what will really be computed? So we'll compute 0, we'll compute 5, that's a complex number, this is real. And then I don't compute this, 10, right? That's conjugate of 5. So here, what do we have here? So we have this one, and this is W, and this one is W squared. Okay. Okay, so it looks like these are being computed. Okay. So let's say 2 plus I wonder though, I think something has to be thrown out, because if these have to be 15 and this is real, then I need, yeah, okay, I see that. So these are 7 complex quantities, that's 7 times 2, 14, and then plus 1 real quantity, that's 15. So that satisfies the degrees of freedom, and that means nothing is thrown out of these things. Okay, so that's good. Okay, so these are 15 degrees of freedom. Now what about these inputs? Are they also 15 degrees of freedom? These are 3 things. That's 3 things are 3. These are 6 inputs, complex, 6 times 2, 12, plus 3, 15. No, that's not true. The first one is real. That's real. Okay, so 3 plus 1, 4 quantities are real. 4 quantities are real. Okay. 3 plus 2, 5, complex times 2. So then I can't have degree 14. Degree has to be 15. So let's say this is real. This one is real. This one is real. Okay. So we have 5 real and how many complex? 3, 4. 4 complex. That doesn't make sense. 4 times 8 plus 5, 13. So no, I'm missing something. Anybody sees what I'm missing? Well, okay, I guess it may be good to go to the paper and maybe just review those kinds of things. Yeah, so it's easy to make mistakes and it's easy to spend more time, but this may be a good time to just quickly go through the paper and then. Yeah.
The 2 lower inputs off of the first 5 FFT real, or are they complex? Like the ones that are actually ones that you didn't already draw.
Say that again.
The outputs 2 and 1 and 2 from the top 5 FFT.
Okay, we will just a minute. We will take a look at those. Well, okay, let's take a look at this example first. This one has 3-point FFTs on the left and 5-point FFTs on the right. Okay, so unlike the one I was working out with 5 on the left and 3 on the right. Okay, so 3-point FFT, first one is real, the next two are complex conjugates, so we throw out those, and the weight twiddles W to the power 1, 2, 3, 4. So the last 5-point is thrown out. And if you look at the top 5-point FFT, the last two, which would have been X9 and 12, are conjugates of 3 and 6. So those are not computed. And these are all complex. So at the output, the degrees of freedom 10 plus 5, 15. At the Okay, I see what happened here. I think I can see. So the mistake I was making is to assume these are real, which they are not. For the only this one is real. For the 5-point, the first one is real. All others are complex. So that was the mistake. Is that what you were saying?
I think so.
Okay, very good. So the 3-point, the last two are complex. Even if I am multiplying by W to the power 0, which is 1, but that's still a complex number. So all these 5 are complex. Degrees of freedom 5 times 2 plus 5 is 15. So that's what is satisfying the canonic property of the 3 times 5. So let's now go back. Now that I see the mistake, let's go back to what we were doing and see if that makes sense. Okay, so can we go back to the paper? Thank you. Okay, so these are complex. These are all complex. So only the top ones are real. So that means these 3 are real. These are all complex. Okay, so 3 plus 3, 6. 6 complex times 2, 12. Plus 3, 15, and that's how the degree of freedom is 15. Okay, so that explains. So let's, you can do 3 times 5 or 5 times 3, and all of you have played with these, what this 3-point and 5-point look like in the current homework, so you have an idea about those things. Okay, so let's take another example where we take some even times odd. So let's take 2 times 3 or 3 times 2, either way. So both of those, let's take both of those. So if I have 3 2-point, Okay, so if we are computing 6-point DFTs, so okay, so how can we think about making these structures canonic if the signal input is real? So what's redundant in here? Do you see anything that is redundant? 2 and 4 are conjugates, right? So 6 minus 2 is 4. So we don't need to compute that. Clearly 1 and 5 are conjugate, so one of them can be thrown out. Okay, what about here? 2 is conjugate of 4. By the way, when we take the 3 point, the last one, this is the conjugate of this one, this is the conjugate of that one. So these don't need to be computed. And as you can see, there's nothing lost in not computing these. 2 is conjugate of 4, 5 is conjugate of 1. Okay, so the degrees of freedom, 2 things real, these are just the real things. These are complex. 2 times 2 plus 2 is 6. What about here? Real, that's 2. This is complex, multiply by W, that's complex, that's 6. Okay, so what about here? Let's take a look. 1 plus 2, 3 plus 1, 4 plus 2, 6. Okay, so that satisfies. There's nothing more we need to do. So that's already satisfied, and that satisfies the data canonic property. Okay, what can we do here? So, so there is nothing redundant if we have 2 outputs coming out. There is nothing redundant. One thing I can say is, so by the way, what are the real quantities here that must stay? 0 is real. What else is real? Anybody else has any guess out of 2, 1, 3, 5? What will be real? X3. So it's always 0, x0 and xn by 2, n is 6 and by 2 is 3. So that's real and that's real. So these two will stay, and eventually we can ignore one of the 2 and 4, one of the 1 and 5. Okay, so that's perfectly fine. Now here is the challenge, however. The challenge is that the degrees of freedom here, 2, 3, 5, 6 and 2, 8. So if we look at the number of degrees of freedom here is 8, because we have 6 wires, but these are 2 are complex, and same at the input of these also 3 plus 1, 4 plus 4, 8. Now that's really challenging. So how do we, so we need to do a little more work. So there's nothing more we have to do in that one, but if I have to make this structure canonic, I need to play with this quantity here, and then I need to exploit a data modulation property. So the data modulation property says that if xn DFT is xk, then xn multiplied by e to the power minus j 2 pi over n k0 n is going to be x k plus k0, right? K plus k0. So if I multiply, so this can be, if you want to think of that, this is xn w to the power k0 n. Okay, so let's say that I had three things A, B, C, and I was computing their conjugate, their DFT cap A, B, C. Okay, so what will happen if I multiply this? Let's say that I pick K0 is equal to 1. If I pick K0 is 1, then what does that mean? A, B times K0 is 1, N is 1, B times e to the power minus j 2 pi by 3, C times e to the power minus j 2 pi by 3. Excuse me, 4 pi by 3, n is 2, so this is n equal to 0, n equal to 1, n equal to 2. So K0 is 1 times 2, 2 times 2, 4. And then if I take the DFT of that, then what will that DFT look like? So if these were A, B, C, that's xk, this is shift left, not to the right. If I shift right, bring them down. If I shift left, so A, B, C, shift left by 1 becomes A, B, C, and this circles back here, we get B, C, A by circular shifting. Okay, so if I go back to this computation here, so I had something multiplied by e to the power minus j 2 pi by 6. So remember that n here is 6. That w is e to the power minus j 2 pi by 6. In the 3-point case, n is 3. And that n is 3. So you have to make sure that you are not confused. And that w squared is e to the power minus j 4 pi by 6. Okay, so we have these things here. So instead of computing, okay, this 3-point DFT 135 is equivalent to 2 pi by 3 and 4 pi by 3. and then A goes to the right, then BC. Okay, so I'm exploiting the modulation property of the DFT to replace this part by this part. So instead of computing the 3-point DFT of these, and again I'm doing that only to satisfy the data canonic property here, so that the degrees of freedom is 6 and not 8. Now, well, we can always argue, has anything really changed? But you look at what is this times that, this is 2 pi by 6, this is 4 pi by 6, minus 2 pi minus 4 pi is minus 6 pi by 6, and the product of these two is e to the power minus j pi, 6 pi by 6 is pi, which is minus 1. So that is equivalent to, so that became minus 1. What about here? Minus 4 pi by 3 is 8 pi by 6, 8 pi by 6 and 4 pi by 6, 12 pi by 6, which is 2 pi, e to power j 2 pi plus minus is 1, and that becomes. So the twiddles that were making our life difficult with these extra complex have disappeared. So these are now replaced by WW squared, are replaced by 1 minus 1. So now the degrees of freedom is exactly 6. That multiplying by minus 1 doesn't include any imaginary numbers. And then finally 3 is a real quantity that stays. I can keep 5 and remove 1, don't compute that bottom one. So the degrees of freedom at the output, 0 and 3 are real, 2 and 5 are imaginary complex. So 2 times 2, 4 plus 2, 6, that satisfies the data canonic property. So I think there is one last example that I can take, which is even times even. So when we have even times even, so let's take an example of 4 times 4. So if we have 4 4-point DFTs, okay, so we are going to compute okay, so what do you think will be the redundant parts for a 4-point? For a 4-point, the 0 and 2 are real. Let's see if I can find the diagram. I see the diagram. Okay, so So 0 and 2 are real, so this is real, and out of these I throw out the bottom. Okay, we throw out the bottom. Okay, so and then when we are computing, so these are all real. The first one is all real, then we can throw out the bottom. So real, complex, real. Okay. So now, so let's just see here 0, 4, 8. So we compute then 1, 5, 9, 13, 2, 6. Okay, so though these two can be thrown out because they are conjugates of 2 and 6. Okay, so surely at the output we have degrees of freedom 16. 2 real things. How many complex things? 1 plus 4, 5. Okay, so 2 plus 4, 6 plus 1, 7. Yeah, 7 times 2, 14 plus 2 real things, 16. Now we have to make sure that the degrees of freedom here and after the twiddles is also 16, and it does require a little bit of work, and it so happens that so by the way you can see that w to power 4 is minus j, so that one is just degrees of freedom is 1, that's just minus j. So let's just go to the computer and then I can show you the diagram, and maybe just we'll take a look at this next time as well. So in that diagram there is a little more work to compute 2 and 6, the w squared taken outside a bracket here and multiplied here, so that this was w squared, this was w to power 6, which is minus j is w to power 4, and then w squared, and then this was w to power, this was w to power 6. So this w to power 2 and w to power 2 taken outside and combined here. So look at that. I do, however, want to quickly go through just maybe over a minute or so what the homework is like. So first two problems are for complex FFT. So for the split radix, I had derived in class the equations for x2r and x4r plus 1. So I didn't do this, I just said that it can be done. So spend a little time deriving the equation for x4r plus 3. Number 2 is a little thought-provoking, and it's talking about how to take 2 endpoint sequences. So how to compute the 2 endpoint DFT. This is an endpoint and this is endpoint, and then how to compute the 2 endpoint DFT using 4 endpoint DFTs, and it's really some manipulation and figuring out things. Okay, it's not trivial, it's non-trivial, it's involved and thought-provoking. Draw the block diagram of a 3-point DFT structure. So you did the 3-point complex FFT, remove the bottom part, remove redundant, that becomes canonic, use the composite idea that I talked about, 3 times 5, 5 times 3, so 3 times 3 is 9, do the same thing, and then do the 9 times 2, further 9 times 2, that becomes 18 points. So play with that. This is talking about another diagram here. So this is talking about how to do 12 point by using the composite FFT 6 times 2. So play with that. Number 5 is simply I started the class with how to draw the canonic structures for 8-point DIT and DIF, RFFT. You do the same thing for 16-point DIT and DIF. And the last one is revisiting the correlation problem from current homework and solving that when the signals are real, still satisfying, the conjugate symmetry. I didn't talk about IFFT. Maybe I'll talk about that on Monday as well. So, surely involved and thought-provoking. So we'll stop with that. Yeah, so I think the canonic paper is very good to read. That's probably the Lau paper. This was Eng J. Lau's master's thesis work. Very different from his PhD thesis. So Lau is a professor in Clemson University. Okay, so see you next class. Anybody needs 2 more hours to do the homework?
2 more hours would save me some time.
Yeah.
Will save you or will not?
That's not going to do much.
What the homework? Did you learn new things that you didn't know before coming to this class? If you are coming to the class and are not learning new things, that's not good. Sorry?
I didn't, what? Decimation and pain, that's fine. Mine is not stable, but I numbered all the pages, so hopefully.
Yeah, I'll take it. You can just put it inside your mouth.
Yes.
我一直对他那个定义。